how the buffer can minimize the pH change when you add in a strong acid or strong base. So inside these buffers, we say the buffer is going to have the conjugated acid and base. So assuming today what you have is one end of weak acid HA and one end of its conjugate base A minus. The same concentration, and then they have high amount of those things inside your solution. For my water system, just pure water. If today I add in 0.1 m HCl into these two containers, I want to know the pH change in these two situations. Delta pH means I want to know the pH after I add in. So let's final pH minus the pH before I add in. Let's start from the easy one. Let's look at the water solution first. pH initial, okay, before you add in any acid into your water solution, what is the pH? 7. So you know this one is actually 7. So the pHi is equal to 7. What is the pH if you have a 0.1 m HCl inside your solution? Since this is strong acid, therefore you know the proton concentration is going to equals to your acid concentration, which is equals to 0.1. pH is equal to negative log of H plus concentration less negative log of 0.1. Therefore, the pH is equals to just 1. This one is actually your pH final, right? Therefore, you know your delta pH. Let me take the absolute value here. So it's going from 7 to 1, right? So the delta pH is going to equals to 6. So now let's look at our buffer. So how do you calculate pH of a buffer? HH equation. pH equals to your pKa minus log acid concentration over base concentration. Every time when you see a buffer solution, go to the HH equation. Let's say we have acidic acid. The Ka is going to equals to 1.77 times 10 to the negative 4. Therefore, you know the pH of your solution will be pKa, which is actually your negative log. Ka is 1.77 times 10 to the negative 4 minus log. What is your acid concentration? 1, right? How about your base concentration? It's also 1, right? So here it will be just 1 over 1. So the first term gives you 3.75 minus log 1. So you know the initial pH, pHi, is just equals to 3.75. Then you add in some acid into your buffer. So once you add in your strong acid into your buffer, basically actually throw in your H plus into your buffer. But the acid always trying to find a base to interact with. So once you throw in H plus, then you know the H plus is going to interact with your A minus. So once they actually interact, what do you have? HA, right? What is HA? HA is actually a conjugate acid of the base, right? We say in the beginning, you have 1 m of A minus 1 n of your HA, right? So let's the initial situation we have, right? You have 1 n of A minus and 1 n HA inside your solution. What you do now is actually you add in 0.1 n H plus. So you know the acid is going to interact with your base. That's going to produce its conjugated acid. So you know the change is going to happen. So right now, who is actually a limiting reagent? H plus, right? Because H plus only 0.1. You have substantial amount of the buffer system. This one will be fully consumed. Therefore, you're going to have minus 0.1 for your H plus, minus 0.1 for your A minus. Then you're going to have plus 0.1 for your HA. So once you reach equilibrium, so you don't have H plus existing now, it becomes 0, right? A minus become 0.9. HA become 1.1. After you add in the acid, you know the things you really change is actually you change the concentration of the conjugated acid and base, right? So right now you can see that the conjugation base concentration decrease a little bit, conjugation acid concentration increase a little bit. Once you know this, you go back to the buffer situation again. pH equals to pKa minus log. Acid right now is actually 1.1. Base is actually 0.9. So pKa is 3.75. This things, I believe, is actually around 0.1. Therefore, the pH final will be 3.65. So in the beginning, we know the pH is 3.75. Right now it's actually 3.65, right? What is the delta pH? Just 0.1, right? So you're actually adding the same thing into a solution. Inside water, your delta pH is 6. But in buffer, you only change 0.1. You can see there's like huge differences between the two. So that's why buffer is actually so important. What is the most famous buffer system? Hint, it's inside your body. Yes, the blood. Okay, what's the pH of your blood? Okay, varies. Okay, depending on how healthy you are. Okay, varies from 6 to 8. Blood is actually the system that keeps us stay about the same every day. Okay, so right now you should be able to see if you have buffer versus water. Buffer indeed can actually minimize the pH change when you throw in a strong acid. Let's go to this question. Suppose that actually 1 mole of HCOOH and 0.5 mole HCOONA are added to water and diluted to 1 liter. Calculate the pH of the solution, where the Ka of the acid is 1.77 times 10 to the negative 4. So that's actually step number 1, right? I did not add in anything. I just tell you, I have a solution with all the species inside the solution, right? So what solution do we have? Acid, base, or buffer? Yes, it's buffer, right? Okay, how do you know it's buffer? Ka will tell you it's a weak acid, right? So what are the key features of buffer? Yes, you need to have a coexistence of conjugated acid and base pair. When you look at these questions, I think right now, most people can see that HCOOH, weak acid, HCOONA. Okay, once these things dissolve, it's going to give you HCOO minus and sodium plus. HCOO minus. Can you see these two are conjugated acid and base? If you can see this conjugated acid base coexisting inside your solution, it is a buffer. From here, from this description, you know it is a buffer. How do you calculate pH of a buffer solution? HH equation. So let's do first one. A, we know we have HCOOH. We have HCOO minus. These are conjugated acid base pair, right? Therefore, buffer. Therefore, HH equation. pH is going to equal to your pKa minus log acid concentration over base concentration. pKa is negative log. Ka is 1.77 times 10 to the negative 4 minus log. What is your acid concentration? 1 mole divided by 1 liter, right? So that is just 1. How about your base concentration? It will be 0.5 divided by 1 liter. It's just 0.5, right? So the first term gives you a number of 3.75. And the second term gives you 0.3. Therefore, the pH is 3.45. Step number 2, you add in 0.1 mole of HCl. So this is actually a strong acid. This acid, okay, I just write H plus, okay, it's going to interact with your A minus, in this case, HCOO minus. That's going to give you HCOOH, right? So right now, you know, initially, you have 1 N of your acid, 0.5 N of your base, and you add in 0.1 mole in liter, that's 0.1 N of H plus. The strong acid is going to interact with your conjugate base that form in your conjugate acid, right? So this guy is the limiting reagent, so you be concerned 100%. So you minus 0.1, minus 0.1, plus 0.1. Once you reach your equilibrium, you don't have H plus, but you have actually 0.4 N of HCOO minus, and then 1.1 N of HCOOH. So let's actually the new acid and base concentration. Can you calculate the pH of this solution? I hope the answer will be yes, right? You still have substantial amount of conjugated acid base. So it's a buffer. So HH equation. So your pH is equals to pKa minus log your acid concentration at equilibrium over base concentration at equilibrium. So there will be 3.75 minus log. On the top will be 1.1. Bottom will be 0.4. And your pH final will be 3.31. So to sum up this type of questions, it's always like two steps. The first step is actually you are giving a solution. Okay, you want to look into your questions and identify. If you have conjugated acid-base pair inside your solution, you know it's buffer, then HH equation is actually your go-to equation. Then you add in the acid, a strong acid, and you know the strong acid is going to interact with your conjugate base, then produce more of your conjugate acid. Okay, so it's going to change the concentration of your HA and A minus concentration, right? So to just update that term, then you can actually calculate your pH.